Okay, let's now implement Thevenin's theorem. Okay, imagine that you have a circuit, and I'm gonna draw it over here. And also, um, you might want to see source transformation theorem before you move on to Thevenin and Norton's theorem here. So, okay, so we have a circuit right here. So say you have this source right here. I'm gonna label it as VS, positive, negative terminals there. You have this resistor over here, and then another resistor over here. I'm gonna label them as R1 and R2. And then say you have uh, some kind of load over here, okay? Okay, it could be anything. It could be fan, um, or speaker, or things like that, okay? And I'm gonna label these terminals as, um, maybe A and B, okay? So the voltage potential difference here across this resistor, which I'm gonna label as RL over here. It would be nice if even though this is already a very simple circuit, it would be nice if we can make it even more simpler by applying Thevenin theorem by converting this circuit into something like this. So say you have Thevenin voltage here, and then the Thevenin resistance, okay, and then you put your load over here, okay. And therefore it will be a lot more easier for you to do the calculations where you can find out the current. IL will be the current flowing across this load. And sometimes, when you are, like I said, this load could be a speaker, or some kind of alarm or buzzer or something. It's important to know those current ratings on those. Therefore, if you can convert something into this, it just makes it a lot more easier to do the analysis and choose a device for an application. Okay, and for that matter, when we have this, Thevenin circuit, we can convert it into the Norton circuit, and that's what we learned in the source transformation theory. So let's get rolling. I'm gonna assign some values here. So say this is gonna be 5 volt. This is going to be 5 kilo ohms right here. 5 kilo ohms over here as well. And then RL, just keep it as it is for now. So there are some steps that you need to follow. Okay. The first step here in implementing a Thevenin theorem is to remove the load. Remove the load. Okay. If any. Okay. Right. The second step is to replace battery or a voltage source with short circuit, okay? Or if you have a current source, then you replace current source with open circuit. With open circuit. And then the third step includes calculate the Thevenin resistance, okay? RTH. Okay, all right. So I am going to look at this circuit right here, okay? And then follow the steps that I mentioned. So this voltage source is going to be replaced by a short circuit. Maybe I can change the color here. Yeah, so this voltage source right here is going to be short circuit. These two dots basically mean you have short circuit. This is just now a wire and nothing else, okay? I have my R1 here, okay? I have my R2 over here, okay? And then I'm going to remove the load so there is nothing basically, okay? All right, now for us, because our goal would be to find out the voltage across this resistance, RL, this load, or a current across this load, we want to look at our circuit from a perspective of a load. Okay, so we're going to look at in this direction. And we look at in this direction, we find that R1 and R2 are in parallel, correct? So if I want to, I can transform this circuit and it may look something like this, okay? Uh, so where I have R1 here and I have R2 here, and this here the load is supposed to be. The first thing I'm going to do now is, the next thing I'm going to do is to calculate the Thevenin resistance. So the Thevenin resistance is going to be, because these two are in parallel, so 1 over R1 plus 1 over R2, and then the inverse of that, I can also rewrite it as R1 times R2 divided by R1 plus R2. R1 is 5 kilo ohms, R2 is also 5 kilo ohms, and 5 plus 5k would be 10k. So therefore I get 25k squared, 10k, this k, one of the k will cancel out with this k, and then I basically get 2.5 kilo ohms, right? That's my Thevenin resistance. Now the fourth step will be to calculate the Thevenin voltage, which we refer to as VTH. Okay, and we can just simply apply Ohm's law here. We know the voltage over here, the across R2, is going to be the same voltage across these two terminals A and B. Okay, so how do we apply voltage divider? So VAB, um, which is also equal to voltage across resistor 2, equals to the supply voltage, which is Vs, times the voltage across which you are trying to find the voltage, which is R2, divided by the total resistance, which is R1 plus R2, correct? Now plug in values, Vs being 5, R2 being 5K, and R1 plus R2 will be 10K. So you get 25K over 10K. K and K will cancel out. So you get 2.5 volts here, right? So your VAB, or the voltage across the load, okay, is going to be 2.5 volt. The last step is draw the equivalent circuit. Draw the Thevenin equivalent circuit. Okay, so let's change the color here. And that circuit will look like, you will have VTH here, okay? Some books, they may also say ETH. Both are the same thing, plus and negative terminal here. You have your RTH here, the Thevenin resistance, okay? And then you restore your load here, okay? You're gonna restore your load here, which was the RL, correct? So ETH was how much? 2.5 volts. 2.5 volts here. RTH was how much? RTH was 2.5 kilo ohm. So you get 2.5 kilo ohm, and RL, so say RL is 1 kilo ohm. Okay, so because the series circuit, say the current flowing in here is IL, apply Ohm's law, IL equals to V over R, where V is the Thevenin's voltage and R is the equivalent resistance for this circuit. And because it's a series circuit, so it's going to be a sum of RTH and RL. So you basically get IL equals to 2.5 over RTH 2.5 plus RL, which is 1 kilo ohm. This is kilo ohms too. So IL will be 2.5 over 3.5 kilo ohms, and that gives you, if you let me, 2.5 divided by 3.5. So you get 0.714 milliamps. Okay, there's no space here, so I'm going to write down over here. IL equals to 0.714 milliamps. Okay, so the current flowing here is 0.714 milliamp in this circuit. Okay. All right. So this is what the goal is to, if you have something like this, again, the next example, we have a slightly complex circuit than compared to how it disappears. We can transform this circuit into something like this, and then it becomes a lot more easier to, get these ratings right here, the current flowing across the load and the voltage across the load. If you are going to convert this into a Norton circuit, then what you need to do here is you need to, so I'm going to do it over here. So this will be a current source. This will be your RTH in parallel with the current source. And then you have this load right here, okay, RL. This is your RTH. And current source will be the Norton current will be equivalent to VTH over RTH. So if you plug in the values from here, VTH was 2.5 volts and then RTH was 2.5 kilo ohm. You will basically get the current, which will be 1 milliamp, right? 1 milliamp. Okay, so you have the Thevenin equivalent circuit, and then you also have the Norton circuit right here. Okay, let's move on to the example right here. And again, in this example, this will be considered as the load. Okay, now I'm going to say this is RL, say this is R1, this is R2, and this is R3. The values are given. Say this is VS. Okay, so remember, our first goal was to remove the load, remove the sources, and replace that. If it's a battery, like a DC voltage, then we are going to replace it with a short circuit. And then if it's a current source, then it's going to be replaced with the open circuit. So let's do that. Okay, so this will be equivalent to saying battery is shorted. Okay, you have resistor R1 here. You have the current source. How do you display an open circuit? In some circuit, you just break the connection, okay, break the wire. So this is the open circuit and this is the short circuit. Now then we have R2 here, okay, and then I have R3 here, and then I have removed the load, okay, and then say this is some voltage VL across the load, and this is my R3. Again, remember, because we would be interested in finding the current that's flowing here. Say this is going to be IL. Okay, so we want to look at the circuit from a perspective of a load. And again, this load could be anything. It could be a speaker or a buzzer or something like that. Okay, now looking at it here, we notice that R1 and R2 are parallel to each other, and then they are in series with R3. Okay, so if I'm going to transform this circuit, make it a little bit more simpler, I can draw it like this, correct? So this is your VL right here. This is my R3, and then R1 and R2 are parallel to each other, okay? And then if I am going to further simplify it, then I can put it down as like this. So this resistor will represent R1 parallel to R2, and then this resistance will be R3, correct? And then this, I can further simplify it by saying something like this, where this resistance is basically a sum of R1 parallel to R2 plus R3. Okay, and that is the Thevenin resistance. So I'm going to label it as RTH. Okay, now let's do the math here. Let's get the RTH. RTH equals to R1 parallel to R2. Let's solve for this first. So this will be R1 times R2 divided by R1 plus R2, and then you add this with R3. R3 is, yeah, let's plug in the values here. R1 is 4 ohms, R2 is 5 ohms, and then R1 plus R2 will be 9 here, correct? Plus R3 is 9 ohms. So 9 ohms. So if I do the math here, I basically get what? I get 11.22 ohms. Okay, and I'm gonna box it so I remember this. Okay, this is my RTH. Cool. Okay, let's now move on to the VTH. Now we calculate VTH. So in order for us to find out the VTH, we're going to have to look at this circuit in a way that we have one node over here, and this is a common node, and this is common to all these branches right here. And this potential is basically, so say if I say this is, you have a 0 volt here, okay? So this tells you that this is connected to the ground and there's a 0 potential over there. And also because, I had removed the load from here, I had removed the load initially. So there is no current flowing through this resistor over here, okay? So whatever the voltage is over here, so say this is VA, okay? That voltage will also be over here, all right? Make sense, right? Also notice that I have 3 amps going into this node. And because there's no current flowing over here, so this will be 0 amp, which is IL. Right now, it's 0 amp. And then we need to apply the KCL in order to find out the value for the voltage across this resistor right here that you see over here. Okay, because we know VA is equals to at this node it's also VA, and whatever the voltage here, that would be the same voltage at this across the load as well. So I can write down as VTH is equals to VA. Okay, now I am going to apply KCL here. So, and also the current is flowing in this direction too as well. So what does the KCL says? KCL says current entering the node equals current leaving the node. Right? Correct? Okay, all right. So the current that's leaving the entering this node right here is basically the potential difference of these two voltages here over R. So this is, I can write it down as Vs minus VA over, and resistance here is 4 ohms, right here, 4 ohms. So remember from Ohm's law, we know that I equals to V over R, right? So the voltage across this resistor is a potential difference. You have 50 volts over here, 50 volt. That means you also have 50 volt here, correct? Okay. You also have current entering here, which is 3 amp. So this will be plus 3 amp. And then you have current leaving over here. And because there's no current flowing over here, all of this current goes over here, right? So what is the potential across this resistor? It is actually a potential difference of VA and this 0, okay? If I say this is VB, maybe, so VB is equals to 0, so that will be equals to VA minus VB over R, and R is 5, correct? Okay. So, and if I multiply this whole equation by, say, 20, what do I get? So I would get 5, and VS is, let's plug in the values first, actually. Let's plug in the values. VS is what? 50. So 50 minus VA, okay, up over 4, plus 3 amp here, and then that equals to, again, VA is going to be how much? VA is, we need to find out, so this will be VA. VB is 0 here, right? So VA over 5. And then remember, we are multiply this whole equation by 20, so I'll just multiply it by 20. So what do I get over here? I get 250 minus 5 VA plus 3 amps equals to 4 VA, correct? Now 250, and also this is going to be 60, right? Correct? 20 times 3 is going to be 60. Let me change that, 60. So 250 and 60 is going to make 310. And then if I move this to the right hand side, I get 9 VA. And if I do the math here, VA would equal 310 over 9. And I basically would get 34.4 volts. Okay, so this is my VA, which is, we know that it's the VTH. Okay, and I can write it down here. So VTH is equals to 34.44 volts. Okay, now if I need to simplify this circuit, okay, and then redraw it, what would that be? That would be VTH, okay, here. VTH is 34.4 volts. Then you have RTH here. RTH is going to be, was how much? 11.22. So you get 11.22 here. And then I am going to restore the load resistor here now, RL, okay. And what was the value of the RL? RL was 6 ohms here. So this is going to be 6 ohms. Okay, let's now calculate the current that's flowing through the resistive load. So now I can just simply apply Ohm's law here to find out this current IL, which will be equals to VTH over RTH plus RL. VTH was how much? 34.44 volts, so you got 34.44 volts. RTH was 11.22 plus RL is 6 ohms. So if you do the math, your IL will come out to be approximately 2 amps. Okay, 2 amps over here. So I'm going to go here. I actually just remove all the labels, and I'm going to redo it so I can just, tell you what all these numbers that we got, all they make sense. Okay, so this is your load here, remember. This is your load, and we just find out that the current flowing through this load is 2 amps, okay, which means the voltage across this load will be 12 volts, correct? Or in other words, here you have 12 volts over here. Remember, you still have 2 amps going in this circuit, in this resistor, 9 ohm. So therefore, the voltage here will be 18. Okay, so you got 18 volts over here, and then you have a potential of 12. That means the voltage over here at this point will be 30. Okay, 30 volt, 30 volt, 30 volt going in, there's a drop of 18. 30 minus 18 gives you this 12 right here. You have the current here across 5 ohm resistor is going to be V over R, 30 over 5. So that gives you 6 amps flowing in this direction. Okay. You also have 3 amps going in this direction. And then you also have, remember, 50 volt coming in from the supply. You get 30 volts over here. That means the voltage across this resistor is 20 volts. Okay, and therefore the current over here will be across this 4 ohm resistor will be 20 over 4, which will be 5 amps, correct? Okay, so you have 5 amps going in. Okay, you have 3 amps coming from here. 5 plus 3 would make 8 amps, right? So over here at this node, a total of 8 amps. Okay, and then 2 amps goes here that flows through the load, and then 6 amps over here goes through this 5 ohm resistor. So 6 plus 2, 6 6 plus 2 makes 8, and that's what you have over here. Okay, so see, from here we actually went to something like this, okay, which was a lot more smaller. And then what we do, we basically try to approximate and then get to the, this part of your circuit. This right here is actually, this whole thing. Okay, so just, help us simplify the network and then help us analyze the circuit. Now, also, I did some simulation. It's the same circuit that we were doing, and also notice, so you get a 50 volt potential power source, 5 amp is the total current flowing, and that's what we had too. The load current, which is a 6 ohm resistor, notice we got 12 volt and then 2 amp current flowing through the load. Okay, so we proved that we did our calculations absolutely right. Okay.